Hi, this is the Chapter 12 lecture, the second half. So in this second half, we're going to cover the null hypothesis and the F distribution. We're also going to learn a new table and review what the stages were for making the calculations. We're also going to look at the effect size for an ANOVA and how to report the results. Lastly, we're going to look at the assumptions and um, how to conduct post hoc tests, which are tests that are required if you find a significant difference with your F statistic. So for the F statistic, our null hypothesis will be centered around 1. So in the T statistic, it was centered around 0, right? So in this one, um, as you can see from the diagram, most of the F distribution tends to kind of like hover near 1 because the ratios that compose the F statistic are made up of variances, right? So those are always positive numbers. So we end up with a distribution that's right-tailed. Um, so all of these are going to be positive. We're going to be working with positive numbers. So we're going to also learn a new table. So the table is based off of the degrees of freedom of the numerator, um, the mean squares between, and the degrees of freedom of the denominator, the mean squares within. So as you can see here on the columns, we have what would be little k, right? So, or not little k, little k minus 1, little k minus 1, which is however many groups you have, right, minus 1. And on the left, we have the degrees of freedom of the denominator, right, of the within mean squares. The bold face represents alpha level of 0.01, and the light face represents an alpha level of 0.05. So for instance, if you were working with 2 degrees of freedom for the between mean squares, and you had 12 degrees of freedom for the within mean squares, then the 3.88 would be the alpha level of 0.05, and 6.93 would be the alpha level for 0.01. So these are the two cutoffs. So we're looking at the 4 typical steps that you would take when you conduct any hypothesis test. And since this is one of the tests that has the longest calculations, it's good to divide it in these ways and to approach it in these stages. By first starting with calculating the sum of squares total, and then the sum of squares within and the sum of squares between. Then you would calculate your degrees of freedom. Then from that you could compute your mean squares between and within, and then finally being able to get to the F statistic. So our measure of effect size for ANOVA is called eta squared, but the concept is the same thing as R squared, so it's a proportion of variance explained. But you can see in the formula that we're constructing it using the sum of squares between as a numerator over the sum of squares total. So when you're reporting the results of an ANOVA, you would report it like this, like with F, and then within the parentheses, you would have the degrees of freedom for the between as the first number, and degrees of freedom within for the second number. And whatever result you got, and then conclude whether it was a significant effect and what your alpha level was. If you computed it with a some kind of software, then you would get an exact p level, and then some effect size. So in this case, it would be eta squared. The assumptions for the ANOVA test are the same that we've seen for the previous tests. So the observations within each sample should be independent from each other. The populations that the samples were taken from should be normal, and the variances of the populations from which the samples were taken should also be equal. And this is a homogeneity of variance assumption that we covered in first introduced in chapter 10. So this is a new idea. So once you conduct an ANOVA test, if you do find significant results, the test itself doesn't tell you which means were the ones that were different. So it just tells you, hey, I found a difference between one of these means, at least one of these means, um, but you won't know which one. So if you do find a significant effect, then you have to conduct a post hoc test to determine which mean or means were the ones that were significantly different from each other. One such test is called Tukey's Honestly Significant Difference, or HSD test. So this is what you do here is that you come up with a single value that um, the difference between the means have to be greater than. So for instance, if you had three different means that you were comparing, if you had three different groups, uh, that you were comparing, then you would take their means and then subtract mean one from mean two, see whether that difference is greater than or not than this HSD value. So this HSD number would be taken from by getting this Q value here, Q value from a table that's based off of a little k and the degrees of freedom for the MS within. And it would require that all of the samples that you're using be of the same size. So the formula looks like this down here. So you would take that number that you get from the table, and you would have already calculated the MS within, and obviously you would have the sample sizes that you used. Um, and you would just compare this number to the differences of the different means, right? Mean 1 minus mean 2, mean 2 minus mean 3, and then mean 1 minus mean 3, right? So take these differences, and if those differences are greater than this HSD value, then it means then those two particular means are significantly different from one another. So you can read more about this in your book. So yeah, that's it for the second half. There's a lot more information that you can read in your book, obviously, but this is, these were the kind of the highlights of the important topics. Um, so in another video, I will do some example problems, 16 and 18. So as you can see here, like 16, these two problems, like they'll require me to do everything from scratch. So you'll see me calculating everything. The examples that we used before were already kind of giving us some of the information, but um, in these videos, we'll just kind of do everything from the beginning. Okay, I'll see you then.